Okay, so let's get started. I've had a couple requests to go over the quiz that was for today with the normalization case study, so I will do that first. Then I'm going to show you how you could have done the hotel case study slightly differently if you had chosen the hotel number and the room number and the date from as your primary key rather than the guest number and date too. It would have changed the normalization process, so I wanted to quickly go over that. And then we're going to get into physical design, which is the last thing that we are going to be dealing with databases. So we will start that today and then finish it up next Tuesday. And 2 weeks from today will be your first midterm. Actually, it will be the midterm. And it will cover everything from the database part of the course. Yes.
Do you have a practice midterm that we can take?
Yes, I will have a. In fact, I think it's already up. Yeah, if you go and look at the exams link, it's already there. Okay, so you were asked to essentially work exercise 14.14 from the book, and you were essentially going through, I was making you work through it in order of the parts. So you were first being asked to identify the functional dependencies, and I gave you a couple assumptions that you could make that the book didn't really tell you. So basically you were looking at a form that was, yes, great.
The instructions said question 14, 15.
On Blackboard it did say 14.15, but it was the question 14.14 from the book.
Yeah, so that's why it's the issue. Okay, so is the issue still that you want me to go over 14.14, or was it that you were confused? Pardon? Okay. So did you figure it out, or did you try to?
I figured it out.
Okay,
I read 14, 15.
I got you. I'm guessing what happened is that the previous edition of the book had it. I apologize that had it like that, and I didn't realize because most exercises never renumbered. Okay, so if you're looking at the, well, I know most of you can't see the diagram anymore, but hopefully it's somewhat in your mind. So the way that, oh geez. Okay. I'm just going to, I can't review the whole thing, meaning there's stuff from the appendix, there's stuff from this figure, so I'm just going to go over it. So the patient number basically determined where the patient was in the hospital, okay? So that meant that it was determining the ward number and the bed number. And while the wards could be unique, presumably bed numbers aren't unique. So you couldn't just say bed number, you'd have to say ward number, and it also determined where it was. And based on the information, the full name was also determined by the patient number. And then since I said that ward names are unique, the ward name would determine the ward number. And the ward number is an artificial key, so it's definitely been chosen so that it uniquely determines the ward name. And then they indicated that a drug number would determine the name, the description, the dosage, and the method of administration. And if I'm not mistaken, morphine could be you could have different units for different patients. So if you looked at the figure, one patient had 10 whatever it was, 10 units of morphine, and the other had 50. So the patient number and the drug number would determine, and the day on which it started would determine essentially the prescription, how many units and what it ran to. And you might have a separate prescription for the patient for another week. So week 1, you might give them 50 milliliters of morphine, and then in week 2, you might only give them 30. So you could have 2 prescriptions for the same patient, but with different amounts of morphine, because you might be stepping it down as they get better. Yes?
How does the drug number determine the dose?
So I believe that that is the concentration. So it's not the, you're probably thinking the dosage is what is given to the patient, but instead they're just talking about the concentration. If you're a chemist, what is the concentration of the medication per volume of liquid? So it's
the book, the same patient had the same drug number for morphine, and then one of the dosages was 50 milligrams per milliliter, and the other dosage was 10 milligrams per milliliter.
No, it was units. So they had the same dosage, but different units. That's what I'm saying is the dosage, I'm looking at it, the dosage is the same. It's 10 milligrams per milliliter in both cases. So that's what I'm meaning. It's kind of how you prepare the formula. So it's always the same formula, but then you give more of the formula to one patient and less to the other.
And we were also to assume that the same drug number would be administered one way.
I believe that is the case. Yes. So the drug number decides the dosage. So I guess you could, if you're going to say that morphine could be applied either orally or intravenously, you'd have to assign the oral form a different drug number than the intravenous form.
That was an assumption we had to make. Is that correct?
I don't think so.
That's how it works.
I'll have, okay, I have to look in the, I don't want to spend 10 minutes trying to dig through the appendix, looking through it, okay? I know that the book's answer said that, so I know that at least the authors of the textbook believe that that's the way it is. Like I said, I didn't review it before I came to class, so I'd have to look through the appendix to see how that was stated in the appendix. Okay, so for the time being, I'll just say that's the way the book meant for it to be. Now, I'm willing to take a look. If you can come up with a specific question, send it to me. I'll take a look at it, okay? But that's how the book intended it. Okay, and then the other ones were not supposed to be functional dependencies. So the method of administration did not determine the units per day. You could actually see that that was false just by looking at the form data, because in one case it was oral in 50 units, in another case it was oral in 10 units. Drugs could be used for different patients, so that should clearly not be a dependency. The start date is definitely not going to determine the finish date, because you can have multiple prescriptions starting on the same day and finishing on different days. The description and the dosage isn't necessarily going to determine the drug number and the name, and that's because the description could be painkiller, and there's many types of painkillers, each of which could have the same dosage. I could have morphine, I could have OxyContin, I don't know what others are out there. Please don't enlighten me. And so the description was just a generic tag like painkiller, and you can't, from that and the dosage, get to a specific drug number. There could be multiple painkillers with the same dosage. And then, like I said, a bed number might be duplicated in different wards. It'd be common in different wards to number the beds from, say, 1 up to something. So bed number 1 could presumably be in multiple wards. And then I guess the feedback also said essentially the same thing. Okay. Do you want me to keep going? Okay. So then you're given wow, I have no idea why that is in there. Okay. But this is supposed to be the normal form for the first normal form for the relation. And so I've given you now what the functional dependencies are. So this is why you couldn't go back, because you could have just answered question 1 now because I'd given you the functional dependencies. And okay, so you have to identify what is the primary key here. And presumably the primary key, if you're given this information, is going to be what? Well, it's not just patient number by itself, because this is medication for the patient. What were you saying, Senia?
The patient number, drug number, and start date.
Very good. It's actually the patient number, drug number, and start date. So essentially, this is a prescription relation. So in order to uniquely identify a prescription, you probably need the patient number, the drug number, and the start date. Not probably. You can prove that from the functional dependencies. So that's the first thing you have to do, is identify what is the primary key, and that's the primary key. Then, just a second. Okay, so this is the primary key. So that means that you're going to find the full functional dependencies whose left side is a subset of this. And which ones are a subset of it? I'll call this 1, 2, 3, and 4. Which ones are a subset? 1 and 4. Very good. So those two, these two right here, will be used to create separate relations. So patient number, what we do when we decompose a relation is the functional dependency being involved in the decomposition, all of its attributes are placed in a new relation. And the left-hand side, in this case patient number, remains as a foreign key, remains also in the original relation, whereas the right-hand side is removed from the original relation. And the reason the left-hand side stays is it's part of the primary key. So just like, let me get through it. So you have to have the left-hand side has to stay because it's a subset of the primary key. So only the right-hand attributes actually get deleted. And the left-hand side in the new relation will be the foreign key that can be used for joining. So in this case, we get that the patient information, that's this one. So patient information is from 1. Drug information is from 4, this one. And then this is what's left. So I've deleted, out of patient medication, I've deleted these attributes, and these attributes have been deleted from the patient medication. Okay? So
ward number and ward name will not go in their own relation because they don't contain a subset of the primary key.
that's right. So they're transitive dependencies. They're going to be what is involved in going from second normal form to third normal form. But yes, they're not involved in the second normal form because their left-hand sides are not subsets of the primary key. Okay? Yes?
Can you be Second normal form is going from eliminating
what's called partial dependencies. So the idea is that the book's kind of unclear about this. It took me about 4 or 5 years to. The book seems to give 2 different definitions for partial dependency. Okay, in fact, I think it does. But what they really mean to say is that any full functional dependency that is a subset of this is going to be eliminated in second normal form. So they're saying, what they're really saying is that this is a partial dependency for patient number and drug number. And therefore, the real partial dependency they're eliminating is this one. And they're doing it by eliminating the 2 full dependencies that can kind of be factored out. Okay? That's the best explanation I can give for what the book is trying to talk about. So basically, the operational way to think of it is, in step 2, the book says you're removing partial dependencies. Well, kind of. What you're really doing is you're removing the full functional dependencies that are a subset of the primary key. Okay, so that's what's really going on. Okay, then in step 3, never mind. I guess problem 3 was, there we go, perfect. I didn't even have to. This leads right into what I was going to talk about, which is that when I did the hotel case study on Tuesday, I said that I was choosing the guest number and the date from as my primary key, but the hotel number, room number, and date from was an alternative candidate key. And so I could have chosen it as the primary key, and that would have changed the way I did the decomposition. Okay, it would have caused there to be 2 dependencies that I would have used to move from first normal form to second normal form, and it would have been these 2. So hotel number determines the hotel name and hotel zip. So you had those dependencies from the case study, and hotel number, this is the primary key right here. So hotel number is certainly a subset, and also room number and hotel number are a subset. Okay, and none of the rest are. Yep. But that's not a proper subset. That's the problem. So when you're eliminating stuff, the keyword is proper subset. Okay? So that was not a proper subset. This is what I call a candidate key dependency. Last time I referred to it as a candidate key dependency. Okay, so it's not used. And here, this is not even a proper subset, so it doesn't work. Not even any kind of subset. Yep, that's why. Yes.
Did you drop quizzes at the end of the semester?
Yes, I dropped 3. So I understand that some of them are kind of difficult. So, okay, other questions about that? Okay, so the point with question 3 was to show you that you could have a different kind of normalization process if you chose a different candidate key as your primary key. Now, as it turns out, you would end up with the same set of relations once you got to third normal form. Okay, I'm not going to go through that, but it would be the case that you would end up with the same set of relations in third normal form, but when you got to second normal form, they would not be the same. Yes,
Is it
Demi?
always going to be the case that when you get to third multifamily, you get the same set of relations?
Not 100% positive. I want to say yes, because all you're doing is removing removing the partial dependencies and the transitive dependencies, and I think you should, but I'd have to sit down and try to reason it out mathematically, which I haven't done. And I'm not going to try to do right now.
Okay.
So in this case, I know it's the case that they would both end up in the same, with the same set of relations. And every example that I've seen ends up in the same set. But what kind of proof does Dr. Planck call that?
By Cosmo.
Proof by Cosmo. So can't be quite certain that that's always the case. Okay. Other
Can I
questions?
ask you a question about
Mhm.
set and normal form?
Yes.
There is the partial dependency in the book that C name is dependent on client number, and it says that it's a partial dependency. But we have only one attribute from the left and one attribute from the right, so why is
Okay,
it
so
partial
which,
and not full?
where are we?
It's
Show me that.
like client number, C name, why is it partial and not full? The second one,
Okay.
if it has only one attribute.
yep. Okay. So, if I don't have a scanner. Okay. So, Senia's question essentially what, Senia, let me boil it down to, it's the same,
It's like word number, word name.
it's where it's being inconsistent. So, it's just like,
Just the
Did
second
you-
one.
well, just a sec. It's just like right here, oh, come on. Right here is calling 1 and 4 partial dependencies
Yeah.
because they're not. This is where the book's definition is inconsistent for partial dependencies. The book first says that a partial dependency is one where the left-hand side has too many attributes. Like this one, it would say patient number, drug number, start date is also right now determining full name, ward number, and bed number. So first of all, early in the chapter, the book says if this is a dependency, then it claims this is a partial dependency because patient number uniquely determines these attributes. So it claims that this whole thing is a partial dependency. Then later, the book turns around and it calls this a partial dependency. And that's wrong.
No, empty set.
Right.
Otherwise, real life is the empty set, which doesn't make any sense.
Exactly. So the book tried to give you two different definitions for partial dependency. Okay, and that's what's confusing it. So it's the same question you're asking there. So first of all, I will not ask you on an exam to give me one of those two forms of a partial dependency. I guess basically what I would say is for the exam, if I say, what is it that goes from first normal form to second normal form? What type of dependency? I want you to answer partial dependency. Okay? But I don't want you to worry too much about
What is partial?
because the book, in my opinion, has loused it up by giving two contradictory definitions for it. I'm sure that they don't care. I'm sorry. It's unfortunate, but I've known enough textbook authors over time to know that they're.
Of course they care, they can change that one thing and charge another $150.
That's a good point, Colin. That's an excellent point. Of course, that's not what they changed. They changed something else that seems irrelevant and charge you another $150. The things they should be correcting, they don't always do. So, at any rate, don't get too hung up on what's a partial dependency just because the book gave you conflicting definitions. Okay.
So
I will tell you what technically, mathematically it is. The first definition the book gave is the right one.
Yeah.
Okay? And the second one they gave for normal form is the wrong one. They should have named it something else, and they didn't. Yes?
can you tell us your definition of partial dependency?
Okay, so my definition of partial dependency is the first one, which is that it is a dependency where that is not minimal, where the determinant on the left-hand side is not minimal. You could eliminate one of the attributes from the determinant from the left-hand side and still uniquely determine the attributes in the
Okay. The same one
dependency.
that's in the notes.
Mm-hmm. Yep. So the same one that's in the notes. Like I said, though, because I find it so confusing what the book did, I won't ask you to define what is a partial dependency on the test. The only time I will expect the words partial dependency is when I say, when you go from first normal form to second normal form, what type of dependency are you using? Please respond partial dependency. Other questions? Yes, Greg.
It's not really the assumption regarding drug number determining the drug dosage. That's actually in homework 5.
Okay.
If it's not mentioned, you have to look under the appendix or that question.
Okay. I'm guessing what happened is I clarified because the book made the assumption in its answer. So, like I say, let me look, okay? I'll see what's going on. Okay, other questions? Okay. And that takes care of the quiz. So that brings us to physical design. So,
Can I just let's
Mhm.
last question.
Actually, I need to get into physical design. So let's ask me after class, okay? Okay. Okay, so it's got two goals basically. So the first goal is you want to map the relations into physical files. And for that, you need to choose a file format. And there's basically three file formats that you can choose. One is what's called a heap. And it's not the binary heap you learned in data structures. It's simply an unordered file. So you just write out the tuples in any order. It doesn't matter. The second type is a B+ tree, which is a variation on the binary search trees. And the third is extendable hash table, which is a variation on hash tables. So basically, there are three types of files, physical file organizations you might use for relations. And we're going to talk about B+ trees and extendable hash tables later in the lecture and on Tuesday. Heaps are pretty easy. You just write out the tuples in the order they're presented to you. Okay, and the second goal is to select what are called indices to aid the query processor. And we will get to that momentarily as well. Before we get to those two things, we need to talk about what makes disk access different than in-memory access. So basically, you probably know through hook or crook that accessing things on a disk is slower than accessing things in memory. Okay? And you have to kind of know some basics of disk organization. Even though they're going out of style, they're still pretty common. So the idea is they're typically platters, okay? Hence the word disk. And the platters are organized into tracks. And the tracks are organized into discrete units called blocks that are of a certain size. In Unix, the typical size is 4,096 bytes for a block, but it can vary from system to system. Okay. When you perform a disk read, it reads an entire block. It doesn't just read the piece of information you want. So a disk read reads an entire block. So already that's more expensive than a typical access to RAM, because a typical access to RAM only reads one variable, whereas a disk read will bring in more information than perhaps you were looking for. If you're looking, there might be 40 tuples on that block, and you may only care about one of the tuples. It will still read the other 39. But there's other things that slow you down. So in random access memory, it pretty much is very fast to figure out where the address allows it to very quickly figure out where the piece of data is. It's the same thing actually in solid state memory. It's very fast to figure out where the data is. With a disk, to figure out, to get it to where you can read it, you need to physically get this block under the read head. Okay? So that requires two actions. Okay, the first action is you have to move the arm of the reader to the right track. Okay, so that's called seek time. Okay, and that's the time to move the mechanical read arm, or read write arm, to the right track. Okay, and can someone tell me, once it's there, can we start reading immediately? No, why not? There's spin time, which is called the rotational latency. So it has to spin under the read-write arm. So it might be that the read-write arm actually is right there. So this track has to spin over to there before it can be read. So that's called rotational latency. Okay, so it's the time for the appropriate block to rotate under the read-write arm. And in general, what do you think the average time is? It's half the, well, it's half, generally it's going to take, on average, it's going to be halfway around, right? So it's going to take about half a revolution on average for it to move under the read-write head. And the changes have not been very fast. So back in 2014, I had times for random access, and before today's lecture I went and updated them and found that essentially random access times have not really changed very much. So random access time includes both seek time plus rotational latency. So for very expensive high-end enterprise disks, it's about 3 to 4 milliseconds. For an average laptop, it's about 9 milliseconds. And for a mobile device like your phone, well, you wouldn't have it on your phone. For a mobile device or a laptop, it tends to be 12 to 15 milliseconds. And those times essentially are unchanged from 2 years ago. Whereas times keep increasing or decreasing rather, access times for random access memory keep decreasing. Plus, actually clock cycles haven't really gone up that much either. But at any rate, even for a high-end disk, you're looking at a maximum of about 333 reads per second. And with today's clock cycles, you're getting close to 1 billion instructions per second. It's not quite that high, but it's pretty high. So you might be getting on the order of around 1 million, we'll just say roughly 1 million instructions can be executed per read. That's pretty substantial. Okay? In particular, that should show you how slow a disk read is relative to a read from RAM. A read from RAM is going to take a few clock cycles, but it's not going to take 1 million. Okay, so it's considerably slower to go out to disk. And the problem is disks are mechanical, whereas memory is not and the CPUs aren't. So they can't really get the mechanics to go much faster. That's why every year it gets a little worse as far as the number of instructions per read. For those of you who read what I'd put up, that textbook was published maybe 10 years ago, and you'll notice what figure it used. 25 million instructions per second is what it was claiming. Okay? And I forget how many reads per second, but I know that the number of reads per second has gone up much more slowly than the number of instructions per second. Okay, and then you see transfer rates. Actually, I did not get an updated figure for that. So even if you were just sitting at the same spot with the read-write head and just reading, so you could just read continuously, you could transfer about 140 megabytes per second from an enterprise-grade hard disk. Okay, that's not even close on my laptop, so I drool at speeds like that. I know that when I connect up a DVD and it's reading something into my laptop, I don't get anything close to 140 megabytes per second. Maybe 140 megabits, but not that. Okay. So what is becoming more common is solid state, and it has almost no seek time. So the time to locate where the piece of memory is less than 0.1 millisecond. Transfer rates have gone up by about 2 times in the last 2 years. So in 2014, it was about 100 to 600 megabytes per second. Now it's 200 to 1500 megabytes per second. That's a huge range, and that's because solid-state memory varies in its quality. Your laptop doesn't have really good quality SSDs. Even if you think it's great, it's nothing compared to what goes into high enterprise SSDs. And one of the big things that makes your SSD so crummy is the write times. So on cheaper SSDs, like in your laptop, the writes are about 10 times slower than the read rates. Whereas for the higher end SSDs, the writes are comparable to the read times. Okay, but most of the time you're booting up applications or your operating system. That's why you love solid state memory. It definitely, if you compare the transfer speeds, they're already at 200 megabytes. Even with your cheap one, it's still better than 140 megabytes. And remember, that's the only way you get 140 megabytes off the, first of all, that's an enterprise grade hard disk. That's not my laptop. And secondly, that's only if the disk arm is sitting there doing a full-on read. It's not. It has to keep moving back and forth in order to perform it. So it's not even going to get up to this 140 megabytes. Okay, so solid state is the wave of the future. How many of you have solid state memory on your laptops? About half of you. Well, believe me, for those of you who haven't had a sniff of nirvana, solid state memory just is amazing. Okay, I just got a new computer. I'd had a solid state machine, went back to a disk, and now have a solid state machine. I cannot believe how much faster it seems than the hard drive. However, even with solid state memory, it's not as fast as access is to RAM. Yes, Greg?
You would want to update your solid state megabytes per second.
Pardon? Really? Then the Wikipedia page needs to update itself. Pardon? What? They did? Okay. So it's now 5,000? Okay. That was, at any rate, I Googled Wikipedia solid state drive, and that's where I got these numbers. So, but I will take Greg's numbers. I'll put a footnote that says Greg Roulet, 50. Tell him. But that's it. When did they release? Okay.
That'll be what you see.
Okay.
You will or will not?
200 to 1,500. So he claims enterprise. Well, but if they just release them this month, I'm assuming that still most enterprises doesn't have them. I'm guessing that they're still, but you're right, they've got to be higher than 1,500. Okay.
Most enterprises are still running off SES connections.
Whatever. Okay. Well, I'll get that updated. Okay. Bottom line is we want to minimize the number of disk accesses. And we're willing to pay a hefty price to do that. So before we get to that, though, one way we can minimize disk accesses is to organize the file, to sort it, just like we do in main memory. Okay? And that type of index is called typically a cluster or primary index. So in both cases, primary and cluster, we're talking about the file is actually physically clustered or sorted using either a primary key or some other key. Now, it may surprise you, but almost all files have what's called a cluster index, not a primary index. Okay? And the reason is most primary keys are artificial keys. And what is the benefit of having a sorted file or a sorted data set? What type of query do you need a sorted data set for? Why wouldn't you always use a hash table? I mean, a hash table has better performance than a binary search tree, yet we still sometimes use binary search trees. Demi.
Hash tables are not sorted.
Correct.
They're not preserved sort order.
Right, but why is that? Okay, so I'm looking for a query that depends on sort order. Range query. So a range query is going to require a sorted. So there's two types of queries. There's what are called point queries, where you're going for only a single piece of data, like give me the information associated with Brad Vanderzanden. And there are range queries, such as give me all employees who make between $20,000 and $50,000. So that's a range query, where a point query would give me all employees that make 20K. Okay, so you need sorted data to efficiently answer a range query. How often are you going to do a range query on an artificial key, like Social Security number? Do we really care about all the security numbers between 0 and something? Greg's shaking his head. Right. It makes no sense. What we're going to be doing our range queries on are things like salary, or in a race database, I used to be a runner, race times. Okay? So generally, we actually cluster on some key that is not the primary key. It's actually pretty rare that we physically sort a file on the primary key, because usually the primary key is artificial and not a good candidate for a range query. So normally we're going to figure out what range query is most common and sort it on that particular key. Then we still want to perform, yes? Yes, branch number is an artificial key, employee number is an artificial key, Social Security number, those are all artificial keys. Okay. Name is not, although it's pretty unlikely you're going for a name, going to do a range query on a name either. Okay. Now, even if we've ordered it, say on salary, we're still going to want to do lookups on other attributes like name. We'll do a lot of point queries. And for that, we would still like to avoid a linear search through the file, because disk reads are expensive, and do a linear read means we're going to do a lot of block accesses. So we'd like to do better than a linear search, and for that, we use what are called secondary indices. So those are indices on non-clustered attributes. And what those look like, conceptually, is you would have, say, BVZ, and you would have something like maybe disk 3, track 8, block 5. Okay, and you might have Nancy with disk 3, track 10, block 2. So the secondary index is giving you not memory pointers, but is pointing to places, the appropriate block on the disk that holds the tuple with that particular name. And so the idea is the index can be searched relatively quickly, and then we can go directly, once we have this address, it's pretty quick, relatively speaking, to find the block and bring it into memory. Yes,
Is
Demi?
it generally the case that your indexes will need to fit entirely in memory in order to get good performance?
No. That's a good question. So Demi's question is, in general, do we need to be able to fit the entire index in memory? And the answer is no. However, we have to then try to make sure that we can get to the index with only one or two block accesses to locate it. And that's where extendable hashing will come in. It will turn out that usually our secondary index is extendable hash table because it usually requires only 1 or 2 block accesses. Okay, but still, 1 or 2 block accesses for the index is better than, say, 500 block accesses to read the entire file.
Okay.
So it's still a win. Okay, so then the question becomes, what do we index? You might think, wow, why don't we, oh, there's a, okay, improves. So cluster indexes improve, just a second. So basically, cluster indexes improve range queries, or improve performance of range queries. Secondary indices improve the performance of point queries. And also, secondary indices can sometimes solve aggregate queries or aggregate function queries without reading tuples. So for example, let's say you had a secondary index on salary, and I asked for the average salary. You could simply read the index and perform the computation on the index. You wouldn't have to read any tuples. Same thing, I might ask for the minimum and maximum salary. I just have to look at the index. I don't have to look at the file itself. Normally, to find the minimum or maximum tuple, I'd have to look at every tuple in the relation. But if I can go to the index, I might just be able to look it up in the index. And even if it's not clustered, the index, well, it should be, actually. It's, well, no. Actually, an index is typically a hash table. So even if it's not clustered, still, it's faster to read an index than it is to read an entire file.
For something like average or sum,
Mhm.
it seems to me that if you wanted to index that, to have that in an index, the way you would do it is to have have the index contain the actual sum.
And then update it, right?
Yeah, the database to update that each time.
I don't know how databases are actually implemented at that level, but it wouldn't surprise me if they don't do something like that. Makes sense that they would keep the derived figure and then just do updates on it like they do views. So, but the point is, you can often, if you don't have that information, you can often solve it just using the index. You don't have to go out to the file. Okay, so question then is, what do we put an index on? Because it seems like this might be an unmitigated good. Why don't we put it on everything? So first of all, let's talk about what we'd put it on, and then we'll see some of the things we might not want to put it on. So you always want to index the primary key if it's not the cluster key. And the reason is that joins are essentially point queries, where you're saying A.name equals B.name, where B.name equals Brad. Well, you've gotten the Brad from B. Now you got to get Brad from A. That's a point query. So joins actually are a lot like point queries. And although you don't perform range queries on primary keys, you perform a lot of joins on primary keys. So it's good to put a secondary index on the primary key of a relation. And for the same reason, you put secondary indices on foreign keys because joins are a frequent operation and they're going to be heavily involved in joins. Then any one that is commonly used in a selection query. So for example, you would tend to put, say, salary. You might index salary. Trying to think of, I would, let's say age was in the database. I don't think you would get a lot of point queries on age. It will come up occasionally, but I wouldn't think someone would search a lot on age. So you might not use age heavily in selection queries, and so you might not end up indexing age. Okay? Anything involved in order by or group by. Because order by means you're going to have to sort it, so it'd be nice if you already had an index perhaps that had it in sorted order. Group by, same thing, if you need to aggregate stuff. So group by is like a range query, right? So group by is like a range query. So if I say I want, sometimes I might be doing a lot of aggregation by branch number. So in that case, I actually might want a secondary index that is organized, sorted by branch number because I know I do a lot of group by queries on a branch. And then other operations that involve sorting. So a union and distinct both involve sorting. Distinct has to remove duplicates. Easiest way to remove duplicates is if you have a sorted set. And union, you can't include duplicates because relations don't permit duplicate tuples, so unions need to eliminate duplicates. The way you do that is with sorting. Okay, and then these two are kind of the same. You generally like to put secondary indices on attributes that are involved in built-in functions because you can solve those built-in functions by just querying the index. You don't have to go out to the tuples themselves. Okay? So that's kind of a good heuristic for what you want to index. Now, as I said, you just might say, well, why don't I index everything? And there are some reasons not to do so. First of all, there are some relations that are pretty small. Even for some big companies, there are small relations. An example of that would probably be the branch relation. Okay, even for fairly big companies, you can fit a lot of information into a block. Okay, at 4,100 bytes, and 100 bytes per record, you could still get 40 tuples into a block. So even a good-sized firm might not have more than 40 or 80 tuples for the branches, or 40 to 80 branches. So we'd be looking, in that case, at a relation that was 1 to 2 blocks. Well, how is an index going to help us? Demi had a good point, which is, can we keep an index in memory? Well, in this case, for such a small relation, the answer is yeah, we could keep it in memory, but what's the point? I mean, reading 2 blocks isn't necessarily going to cost you. Yes?
For a small relation, wouldn't it, at least in some cases, be better to just keep the whole relation?
Again, it's up to, okay, it depends whether you have dedicated server machines. The database is going to depend how it's set up. The answer, Demi, is maybe.
Okay.
It is, I mean, on your computer, on your laptop, which is sharing memory with a lot of other things, it might not be able to cache it in memory.
Okay.
But on an Oracle setup where it has devoted servers, the answer is probably yes. So it just depends. But at any rate, it's generally not a good idea to index a small relation because the index isn't saving you any time. In fact, if the relation is one block, it's only going to waste time because you got to read the block anyhow. Okay? This one, the second one, is a lot harder to judge, and oftentimes it's just a tuning thing. Once you have the database up and running, an attribute or relation that is frequently updated. So there's some attributes, like if you're doing, or relations like inventory, inventory gets updated a lot. So it's not clear whether you want to keep it sorted, whether you want to keep it indices on it or not. Probably you do because people are constantly looking at your inventory. So even though it's being frequently updated, you still probably want to put an attribute on it. But it's something to be weighed because every time you change the attribute in the relation, you have to change it in the index too. Okay? This one, though, is important. It often catches students. So an attribute, if the query will always retrieve a significant proportion of the relation, it doesn't make sense to index it. Okay, the example I like to give is, so generally you want the expected number of records per block to be much, much less than 1. Okay, let's say that each block holds 50 records and you expect a query, so 50 records, and you expect the query to return 1% of the database. That seems pretty tiny. Right? 1% of the database seems tiny. But if there's 50 records per block, on average, how many? Let's see. Let's think about this. You got 50 records per block. Let's say you have 10,000 records. So that is 200 blocks. Okay, 1% of the file is 100 records. And if it's evenly distributed, how many blocks are we probably going to read roughly? If the records we want are evenly distributed over the database. How about 100? It's going to be about 100. Randomly speaking, some of them are going to collide to the same block. I think actually the number is more like 78, but still, that's, even though we're only retrieving 1% of the records, we're retrieving close to half the database in terms of blocks. So in fact, you can't go by the percent of the database. You have to go by what I have here, which is expected number of records per block. It has to be much, much less than 1 in order for the index to be worth it. In this case, we're looking at a half record, 0.5 records per block. That's nowhere close enough to be indexing. Okay, so you got to be knowing how many records are likely to come back from your query. Okay, now most queries are point queries, which means that it's going to be effective. The question, this comes up only on range queries, because only range queries, well, joins can do it, but in some sense, range queries are the ones where you may be returning a bunch of records. Okay, and finally, we want to avoid indexing attributes that consist of long character strings. Does anyone know why? It's Not so much that as if it's a long character string, it's probably the attribute that takes up most of you. You're probably basically storing a second database. So if your tuple is 100 characters and the long character string is 50 of those, then your index will be half the size of your database. So it's a memory issue. If you index a long character string, the size of that index will be probably a good, roughly comparable to the size of your database. So unless you love spending a lot of money on disk, probably not a good idea to be indexing super long character strings. Yes?
Why can't you do just, even if it's 100 characters, you only do an index of 1 or 5 or...
Okay, so the problem is if it's long character strings, let's say it was street addresses. Okay, each street address tends to be unique. Okay, so you're going to end up with one for every tuple, and you're going to gobble up a lot of memory. Yes, Demi.
Does the index actually have to store, thinking especially for hash indexes, does the index actually have to store the value of the attribute, or can it just store pointers to the attribute?
So it's a good question. So Demi's question is, if it is a hash table, does it actually have to store the attribute key, or can it just store the hashed value? And it problem is, if it doesn't store the key, then you're going to have to go out to the actual tuple, and you may discover it's a miss. So there's a trade-off. I would say generally the key would be stored in the index. Also, the second reason is you're trying to perform some kind of aggregate function on it. You need the key in the index. So I'd say yes, you typically keep the key in the index. So you can't really get around it. Okay, and the book spends some time talking about analyzing transactions. My experience is that will drive you crazy. Typically what you do is look at a few of the most common transactions that you think will happen. Try to optimize those, and then you just bring up the database and you start running it, and then you start monitoring it and you have basically performance monitors on it. You see which queries are slow, and you start looking at why, and you figure out what you can do to improve the performance of those queries. So a lot of it is an art form, okay, where you make your decisions based on these rules of thumb right here, the things to index and the things not to index. You make your decision, you make your choices, you bring it up, you start running it, and you figure out what works and what doesn't. Dr. Planck says one of his pet peeves is that people overthink problems and they'll spend forever before they start writing a program. Now, you should spend some time before you start writing a program, but some people will be like Hamlet, to be or not to be, and can't make a decision. And oftentimes you just program it up, see if it works, and if it does, great, and if it doesn't, you change it. And that's kind of how a database works. You use these rules of thumb. If it works great, great. If certain things aren't working, take a look at it and fix it. Okay? So that's it for today. On Tuesday, we will look at B+ trees and extendable hash trees and how they can be used to physically organize the keys in a file. And we'll find that B+ trees are used for cluster indexes, and extendable hash tables are used for secondary indices.